Here we're going to look at a few applications of functions where making a table for the function could prove useful. If you recall in a previous section, we saw the application where Peter rents a car for $100 a day, and he's being charged an additional $1 per mile. Okay, so we looked at this earlier and we found out that our function describing this situation is described as f of x equals x plus 100. Where x equals the number of miles driven. This is our cost function. We can find the cost of the rental by plugging in the number of miles that Peter drives. And this makes sense because $1 per mile, so 1 times x will give us this part of the cost, and he's charged a $100 flat rate, so we just add them together and we get our answer. Well, let's see if writing a table for this function, for this situation, will actually will make things easier for us. So we have f of x and we have x. X is our independent variable. F of x is our dependent variable because it depends on the value of x. So let's pick out a few values for x. Let's say Peter doesn't drive it at all. Doesn't drive the car at all. So he pays the $100 flat rate, doesn't drive any miles, so he just simply pays $100. Now we can do this in our head, and it's very intuitive because this is a very simple example. But what I'm more interested in is the numerical function, the math behind it. And what we simply do, x will equal 0 because he drives a number of 0 miles. So what we're finding here is f of 0. We're substituting in 0 for x. So 0 plus 100 will give us 100. Now this seems like a little more work than just doing it in our head, and that's just because of the simplicity of the example. But when we get into more complex functions and larger numbers, we will actually see that the function will save us lots and lots of time and lots of work. So let's get in the habit of actually using this. Let's say Peter drives 10 miles. Well, what we're looking for is f of 10. So 10 plus 100 is 110. If he drives 20 miles, we're looking for f of 20. So 20 plus 100 is 120. If he drives 30 miles, we're finding f of 30. So 30 plus 100 is 130. And if he drives 50 miles, we're looking for f of 50. So 50 plus 100 is 150, and so on and so forth. Okay, so what's the usefulness of this table? Well, what we eventually want to get to when we're talking about a function is we want to graph it. We want to graph the function on the Cartesian plane because that it gives us a better idea of what's going on. It gets a better idea of the trend of the function. It gives us a visual representation to describe what's actually happened in a particular situation. And when we write out a table of values for our function, we're actually writing out points on that line of the graph of the function. Here we have the point 0, 100. Here we have the point 10, 110, 20, 120. So for the particular x value, we have a particular f of x value. So we plot these points and just connect them with a line, and that's how we graph our function. So that's the end game. So there's actually 3 steps. We want to find our function, write a table of values for the function, and then we can easily graph the function. So right now we're working on getting more familiar, more comfortable with the second step of actually writing a table of functions. Okay, so let's look at a few more examples. A computer manufacturer sells 2 million computers in its first year. So 2 million computers in year 1. We're told that the number of computers sold doubles each year. So we want to write a function in table format that gives the number of computers that are sold per year as a function of how old the company is. Okay, so let's go ahead and define a few variables. We have we're going to let x equal the age of the company. And that's going to be defined in years. Age of company in years. So that's our independent variable x. So our dependent variable f of x is going to give us, well, what we actually want to find out. We want to know the number of computers sold number of computers sold in a certain year. And this is going to be in millions, since we're actually dealing with computers sold in terms of millions, and this will actually save us a bunch of monotonous zeros and make our numbers, more friendly. Okay, so let's draw a table about this. So we have X, which is the number, or the age of the company in years, and F of X is the number of computers sold in a specific year. So let's start with 1. Well, we know in year 1 they sell 2 million computers. Okay, so let's say we want to find out the number of computers sold in year 2. Well, we know that the number of computers sold doubles each year. So in year 2, they sold twice as many computers as year 1, so we just double 2. In year 3, we just simply double 4, the previous year's output, so that's 8. In year 4, we just double the previous year's output of 8, which is 16. Year 5, we just double 16, which is 32. Year 6, they sell twice as many as the previous year, so we have 64 million, and so on and so forth. Okay, we're actually keeping the applications, these examples, fairly simple, just so we can get an idea of what we're looking for and why we're actually writing a function in terms of a table. Because here, if we want to make a business representation of a presentation, we want to use it in graph format. We can plot these points, and we can actually see the trend that we're selling twice as many computers a year, and we can see what that looks like. And we can see how many computers we'd sell in year 20 if the trend keeps up. So tables are very, very useful, and we eventually want to use them to help us graph a function. All right, let's look at another one. Let's say Dean works at a feed store and he makes $8 an hour. We want to make a table showing his earnings for the following input values. So we're going to let X equals hours worked. These are the amount of hours that Dean works. And we want to find what's his income, what's his earnings if he works 15 hours, if he works 20 hours, if he works 30 hours, and 40 hours. Okay, so we've limited our domain to these following values, and we want to find the range, the f of x. The f of x is going to be his earnings. We're interested in his income in dollars. So let's go ahead and make a table of this and see what we got. So we have x and f of x. X is the hours worked, f of x is his earnings in dollars. Okay, so the first one is 15. He works 15 hours. Well, we simply find his earnings by multiplying 15 times 8, which gives us 120. If he works 20 hours, we multiply 20 times 8, which is 160. If he works 30 hours, we multiply 30 times $8 an hour, which is 240. And if he works 40 hours times $8 an hour is $320, and so on and so forth. Okay, so if we want to, if Dean wants to make a graph of his earnings for the year, dependent on how many hours he worked, we can use these points. We can plot these points on a graph, and we can connect the dots, and that will actually give us a graphical representation of his income throughout the year. Okay, so we can see where that's very useful. Let's squeeze in one more here. Let's get the area of a triangle problem. The area of a triangle is given by the following area formula. We have A for area equals 1/2 times base times height. If the base of a triangle is 3 feet, we want to make a table showing the area of a triangle for the following heights. So we're given the following heights of 2 feet, 4 feet, 6 feet, and 8 feet. Okay, so let's go ahead and make a table showing this information. Our independent variable is going to be height, and our dependent variable is going to be area. Area we can also call f of h, because we defined our independent variable as h, so our dependent variable is going to be f of h, where our height is 2, 4, and 6. So let's start with 2. What we're looking for is f of 2. F of 2 equals 1/2 times our base, which is 3, times our height, which in this case it's 2. 3 times 2 is 6. 6 times 1/2 is 3. So our area is going to be 3. And this is going to be in feet squared, or square feet, however you want to say it. It's the same thing. So the area of the triangle with a height of 2 and a base of 3 is 3 feet squared. All right, let's do the next one. Let's see what will be the area of the triangle if the height was 4 feet. We'd plug it into our formula here. We have 1/2 times 3 times 4. 3 times 4 is 12. 12 times 1/2 is 6. So if the triangle is 4 feet high, the area of the triangle would be 6 square feet. Let's take a look at h equals 6. We'd have 6 times 3 is 18. 18 times 1/2 is 9. The height of the triangle is 6, so the area of the triangle will be 9 square feet. And if it's 8 feet high, 8 times 3 is 24. 24 times 1/2 is 12. So if the height of the triangle is 8 feet, the area of the triangle is 12 square feet. Okay, so we're making tables for our functions here, and we just want to see the usefulness of this, because this is actually the middle step. We're actually from where we want to start to where we want to go. We want to start with a function, and we want to graph a function. We want to see what it looks like, get a visual representation, and see where it's trending to. Well, in between those two steps, we have this middle one where we want to write a table of values for our functions. And in this table, we actually have points on that particular graph. All we do is graph these points and connect the dots with a line, and that gives us our function. Okay, so very useful. We'll actually be doing that pretty soon, so I'll see you in the next video.